Hi, today we're going to look at chapter number 4, Newton's law of motion. Okay, Newton's law of motion. Newton has 3 laws. Okay, so before we look at those laws, first we must understand the word force. Okay, so what is force? Force is something that can change the shape of an object. Okay, for example, a piece of plasticine, you can actually change the shape of plasticine by applying force, by pressing, or by pulling, or by twisting. Okay, this is what force can do. Other than that, force can change the direction of motion of an object. Object that move in a certain direction, you can change the direction by applying a force. Okay, so when you say change the directions of the motion of the object, it involves you directly change the direction, or the force is applied in the same direction or in opposite direction. So if the force is applied in the same direction or in the opposite direction, you are causing either acceleration or deceleration. So that one is also under the change the direction. But force can also change the velocity of an object. Okay, so that is roughly things about force that we actually encounter in our daily life. Alright, so that is what force can do. So force, normally we have a symbol F. Okay, and SI unit for force is Newton. Okay, is Newton. Alright, so that is the introduction for force. So when you are asked about is in a very normal daily life, sometimes we misuse the words Newton with one more thing, which is called the mass. So when you are asked to fill a form, normally ask what is your weight. When they ask you what is your weight, actually you're supposed to answer your answer in Newton, not in kilogram. But it's understood that when we say when let's say your weight is people say that your weight is about 65 kg, so it's understood that you just simply multiply by 10 in physics to get a 650 Newton, right? But officially it is wrong when you say weight is in kilogram, because the kilogram is a unit for mass. Alright, so that is something about force. Now number 2, we need to go into the first law of Newton's. Okay, Newton first law. Okay, so Newton first law, it is also called the law of inertia. Okay, the law of inertia. It has something to do with the property of an object, okay, or the reluctance of the object to move when a force is applied to it. Okay, so when you say the reluctance of the object to move is not entirely correct, because sometimes not to move is also a concept of inertia. Alright, later we'll look at example inertia. Okay, now Newton's first law states that an object will always try to maintain its original states of motion if no external net force, no external net force apply to it. Now the important thing is no external net force apply to it, and then another word is maintain its original state of motion. When we mention original state of motion, it means that the object can be initially, number 1, at rest or stationary. Okay, and then at constant velocity. Either one of these conditions, that is the original state of motion. Okay, so that is number one. Number two is this. Okay, when you say no external net force applied to it, that means when you look at the total force applied to the system, it is equal to 0. Alright, so there are two conditions which actually come from this statement. So this is called the first law of an object. Now, to give you one very simple example on the first law of the object is, for example, you have a duster. Okay, you put it here. So I go out from the room, and then after 100 years I come back, this object is supposed to be here if there is no external net force applied to the object. That means initially it is at rest. After a certain period of time, it should be in the same condition at rest. So for example, at rest, no force applied to it, so it should be at rest. And then the second one is, if you are in outer space now, so you're in outer space, object that move in outer space or far away from a planetary system, from the sun and so on, they are not subjected to any force. If that object is already moving with a certain velocity, it will keep doing it for the rest of the time. If no net force applied to it, the force is equal to 0. Alright, the net force equal to 0. So then, for example, an asteroid, and this asteroid is actually being projected from some other collision, and it moves away from its star system. So it moves in a straight line for like millions of years. It's going to behave like that for millions of years. Okay, so another cruel example is, let's say our class go to outer space, and then we are far away from our solar system. There's nothing around us, very far away. You can't see even anything nearby. So I just simply open the spacecraft door. I kick one of you out. Yeah, I kick one of you out, and you're going to fly in a straight line, whatever star you have. And after 1,000 years, people discover you are still moving like that for the rest of your life, right? If you still survive, 1,000, I don't think so. All right. So that is first law. Okay, first law. So application of first law, or the concept of first law, actually we apply a lot in our life. For example, when you need to like dry a wet umbrella, what you normally do is you swing it very fast and then you stop it. Okay, or some people like to open and close at a very high speed. So the reason is, when you are spinning the umbrella, all the water droplet is moving at high speed, and then when suddenly you stop the umbrella, all the water will try to maintain its constant velocity motion. And when you stop spinning umbrella, the water droplet move on with the same velocity and fly away from the umbrella, and that's how we deal with a wet umbrella in a condition like that. And then other than that, another one is in a bus. Okay, when you are stepping out on a bus, if you are standing, the north seat you are standing, you have to be very careful when the bus is moving forward, because when the bus is moving and you are standing without holding on to anything, you will finally end up in behind the bus. Okay, and then the opposite is, if the bus is already moving at, let's say, 60 km/h, and you are not holding on to something, maybe you're chatting with your friend, suddenly the bus come to a stop, and the first thing you realize is you're kissing the windscreen in front of the bus. Okay, so that is because of the first law. Okay, and that condition, okay, we have another concept that we have to look into in more detail, which is the word inertia. Okay, so now we're going to look into what is inertia. Okay, what is inertia? Okay, the concept of inertia is the reluctance of an object. Okay, there are two possibilities. Is the reluctance of an object, number one, to move. Okay. Number 2, to stop moving when an external force is applied. Okay. So for example, you have a moving object. Okay. So let's say we start with a pendulum. Okay, we start with a pendulum. All right. So pendulum from the ceiling. This pendulum 10 kg. Okay. The mass of pendulum is 10 kg. Now I ask one of you to push a pendulum. Well, when you start pushing the pendulum, a 10 kg pendulum is not so easy to move it because it's very massive. So when we say very massive, actually you can actually feel the reluctance of the pendulum to start moving when you are actually pushing it from one other side, from one side. So that reluctance of the object to move is felt by your finger as something that is actually pushing back to your fingers, right? So that is called inertia. Okay, inertia. So now we can see that when the object is in a stationary condition at rest, it's difficult to start it moving. So that is the first statement. Okay, is the reluctance of the object to move when a force is applied to it. Now the second scenario is now the same pendulum. Okay, that pendulum is already swinging. Okay, already swinging. Now I ask some of you to stop it. It's the same pendulum which is 10 kg. Now I ask you to use a finger to stop the pendulum when it is swinging like that. Okay, so oscillating like that, you use your finger to stop it. Well, it's not that easy to stop. You might break your finger. Okay, you might break your finger. So that is the second statement. When the object is already moving at constant velocity, well, not entirely constant velocity, but it is moving. If you want to stop it, okay, it's not that easy. Okay, because it has mass and then it has the reluctance to stop moving when it is already in motion, right? So that's the second statement. The inertia is the reluctance of the object to stop moving when when an external force is applied to it. That is your finger. All right. So that is one of the this is one of the very example to explain the scenario of the words inertia. All right. Okay. Now, how do we measure inertia? Inertia, okay, is measured by mass. Okay, is measured by mass. We know something about the relationship between the inertia and the mass is the inertia is directly proportional to the mass. The larger the inertia, the larger the mass. Okay, so for example, you are crossing a road, okay, and then there is a bicycle, okay, rushing towards you. It's actually quite easy to stop the bicycle by pushing like that. You won't get hurt that much. But compared to a lorry, 5-ton lorry moving at the same speed, I don't think you dare to stop the lorry. Okay, you'll be carried together with a lorry, or we call that one accident. It might be a deadly accident. So that is deadly because the mass is huge, the inertia is huge, and it's very difficult to stop it. Alright, so that is the concept of inertia. Alright, so inertia is measured by mass. So as long as you know that the mass is huge, we know that the inertia is huge. So that is the concept of inertia. Alright, so after that we're going to look at Newton's second law. Okay, so Newton's second law is a more quantitative law. Okay, it's a more quantitative law. So this law actually allows us to calculate a lot of conditions, okay? A lot of things, especially it has something to do with what we call that the relationship between the force and the acceleration. Okay, we already know what force can do. Force can change the shape of the object. Force can change the direction of the motion of the object. Force can also make things move faster or make things move slower, which we call acceleration or deceleration. So first we look at the second law of Newton's. Okay, so this second law states that the force, okay, the net force is directly proportional to the rate of change of momentum. Okay, so in equation we can write something like this: net force is directly proportional to the rate of change of momentum. Okay, P is momentum and your momentum is equal to mv. Now we change it into equation, we change this become k dp dt, and then from definition our k is equal to 1. If you want your force to be 1 Newton and the rate of change of momentum is 1 kilogram meter per second, so our k is defined, okay, equal to 1. Okay, we don't want to look into more detail about the k. So our F is now equal to dp dt. Now there's a little bit of mathematics here. Is going to involve differentiation. And as we know, momentum is equal to mv. So we have this. You have to differentiate mv against t. So from here, we continue to this here. So the F become m dv dt plus v dm dt. And since the rate of change of velocity is acceleration, so our equation become ma plus v dm dt. Okay, so if you look at this equation, okay, we seldom use this equation because it does not involve all the conditions that we have. This is called the rocket equation. Okay, rocket equation. Okay, now in our daily life, our dm dt is equal to 0 or very near to 0. dm dt means the mass loss of our system. For example, when you are moving around, you lost weight, you lost mass. Well, compared to your body mass, the amount of the mass loss from your sweating, your urine, your respiration, everything is very small compared to your body mass. And then you might say that, how about car? Car that run on petrol or diesel, they might lose the fuel, okay, after they run for quite some time, but the fuel is like maybe like 10 kilogram, but compared to the size of the car, which is you're talking about hundreds of kilograms, that is very small. Okay, so you can assume that dm dt equal to 0. So in that case, when dm dt equal to 0, our equation is F equal to ma. And I believe this equation you have learned it in actually from 4, from 5. Okay, this is actually the outcome from Newton's second law. But this is not the definition for Newton's second law. You cannot write this one when you're asked, define Newton's second law. You say that Newton's second law is equal to F equal to ma. That is entirely wrong. That is the outcome in a special case where dm dt is equal to 0. Alright? So your definition is this one here. Okay? And then from a little bit of mathematics, and then we get F equal to ma. Okay? So that is Newton's second law. Okay? Now come to the next law, which is Newton's third law. Okay? So Newton's third law also, we use it actually quite often in our daily life, but most of the time we don't realize it. We actually take things for granted. It will happen that way. So number 4, we have Newton's third law. Okay, Newton's third law. So Newton's third law states that every action, okay, will have an equal but opposite reaction. Okay? Every action that you do, or every action in nature, will have an equal but opposite reaction. Okay? Just like, for example, I'm standing on the floor. Okay, so my weight, which is the force of gravity, is actually pulling me down. That is the weight, which is equal to mg. Now, if there's no other forces acting on my body and there's only gravity, then I'll pass through the ground and go to the center of the earth. But that's not happening. I'm still here because I'm standing on something that pushed me back. So we have this reaction from the ground. Okay, so this reaction, normally we call it normal reaction. Okay, so this is same magnitude as our weight. So that if you look at the mathematics, if your normal reaction from the ground is the same as the weight, the total force is equal to 0. So when your net force is equal to 0, you either not moving or you are moving with constant velocity. And since initially I'm already not moving up and down or vertically, so my net force is equal to 0, so I'm stationary. Vertically, I'm stationary. Okay, so that is action, and this is our reaction. Alright, so this is one of the example. Other than that, for example, you have some guys leaning against a wall like this. Okay, so this is sometimes people like to do, nothing to do. They leans against like that. So you might have this force against the wall. This is a force against the wall, and if the wall is a solid wall, then you're going to have another equal but opposite direction, and that force is the opposite force that you apply. How big is this force depends on so many factors. It depends on your angle, your weight, and then how far you lean out from the wall and so on. So these two have the opposite direction. So be careful. You have to know that when you apply a force like that, you have to make sure that that wall can support the force. If you're in Japan, be very careful because most of the walls of Japan are made of paper. Okay? You don't want to break people's wall by simply leaning against it. Or maybe you're like leaning against a wall that is not strongly supported, like just a piece of plywood, and then you fall over because of the force that you apply. So you see, that is the Newton's third law. Action, reaction. Action, reaction. There are so many examples that we can have actually. Okay, so this is chapter number 4, Newton's law. Okay, Newton's law. Now, where can we apply this Newton's law in our physics, in our daily life? Well, there are a few applications. Okay, we'll look at it one by one. Okay, application of Newton's law. Okay, so the first application of Newton's law is what we call that one, the free body diagram. Free body diagram is a technique used to simplify or simplify object in a complicated system. For example, when I draw a humanoid, okay, humanoid on the floor to show you the forces, it might take time. Okay? It might take time, and it might not look so beautiful, okay, because I'm not an artist. Some physicists are artists, right? So I will just simplify the object that I'm interested with simply a shape. For example, this diagram can actually be simplified like that. Okay, and then the force can actually be simplified like this. Force are not actually simplified, weight and normal reaction. Okay, and then this is one of the example of free body diagram. And then free body diagram is more applicable when you come to a situation when there are more than two forces involved. For example, you have an object. Okay, you hang it from a ceiling, but you pull it sideways. Okay, so for example, a pendulum. This pendulum is pulled sideways with a force. Okay, with a string here. So you see, this pendulum actually experienced three forces. Okay, three forces. So number one, of course, is the weight of the pendulum, and then number two is the tension in the string that hang the pendulum. Number three is of course another tension, okay, another tension that pull the pendulum sideways. But since this is a pulling force, we change this one into F. If you got more than one tension using the same T, then you use substrate 1 and 2 and so on. Alright, so now this diagram we can actually simplify into something that looks like this: 1, 2, and 3. So you see, the object is not in the picture. Okay, when you do like this, this is called the free body diagram. Okay, free body means the object is free, it's not there. Alright, so this is a free body diagram. Well, there are so many situations we can use a free body diagram like this. Alright, but normally in your diploma level, you are only given up to about 3 forces involved. Okay, 3 forces involved. Okay, so this is one of the example. Number 2 is we apply Newton's law in horizontal surfaces. Okay, horizontal surfaces. Okay, horizontal surfaces are like this. Okay, the surface can be having friction or non-friction. We call rough surface or smooth surface. So we have an object, okay, and that object might have mass. So when object is being pulled by a certain force F, and there might be some friction involved here, so the net force, okay, the net force on the object is equal to F minus F. Alright, so this is one of the example in horizontal surface. Okay? Horizontal surface is that surface does not have any angle with respect to any direction. Okay, the horizontal direction, the angle is 0. So now, situation like this allow us to calculate the acceleration of the object by using the outcome from Newton's second law. Alright? For example, if I give you the mass m and I give you these 2 forces, okay, and then I ask you to calculate the acceleration, then you can use this equation. Force is equal to ma. Outcome from the special case of Newton's second law. So the net force is equal to F minus F. This is net force, and it must equal to ma. So from here you can get your A, F minus F over m. So that is how we get the acceleration of the object in this horizontal surface. Alright, so if you already know this acceleration, you can use the equation, okay, v equal to u plus at, v squared equal to u squared plus 2as, s equal to ut plus half at squared, and s equal to half u plus v times t, to calculate the rest of the parameter that you are asked. For example, an object starts with rest, and then you need to find how far does the object move after a certain time. Then you can use this equation, because from rest u equal to 0, acceleration can calculate with condition you know the mass of the object. Alright, so that is how in horizontal surfaces we can apply Newton's law. Okay, very straightforward. And the last situation that we can use is inclined plane. Okay, inclined plane meaning that a surface that is actually tilted up a little bit. Okay, so that is number 3, inclined plane. Okay, inclined plane, that means a surface with a angle theta. Okay, and if the surface is smooth, then we don't have any friction. Now when you put an object on a smooth surface, okay, and the object have a mass m, this object actually experience a gravitational force, and this is the weight. Okay, this is the weight, which is the mg. Now, this weight mathematically can be split into two components. Okay, into two components, and this angle here is theta. So now this component, number one is this one. This component here is parallel with the surface, inclined surface, and I'll call this one W parallel. And another component here is this one. This one is 90 degrees from the surface, so this is W perpendicular. Okay? From analysis of mathematics from geometry, we get this one is equal to W sine theta or mg sine theta. So that is our parallel component. The perpendicular component is W cosine theta, which is also equal to mg cosine theta. We don't go into detail about how to get the equation. So these two equations is the splitting of the weight of the object on an inclined plane. So now, if you look at the force, this force here actually try to pull the object downward. If the surface is frictionless, no friction, and you just let it go, the object will actually slide down. Okay, it slide down and accelerate downward because it has a net force downward because there's no friction. And then the second component, which is the perpendicular one, it try to hold the object onto the surface. Okay, so when you hold the object onto the surface, so the object does not float. Alright, now that is our inclined plane application. You can actually apply this scenario same like this one, except the force component have a sine theta. Alright, so that is the application of Newton's law on these three scenarios. Okay, the first one just now, is a free body diagram, and then the second one horizontal surface, and the third one is an inclined plane. Alright, so that's it for this chapter number 4. I see you in the next session. Thank you.